All right, so the next hour now, our goal is going to be to bring all those layers that we processed up until now together into one script, export or merge all that into one object, export that to file, and then also validate, especially the yield stability zones that we created using the layers that we processed as well. So that's going to be a new exercise. When you download it from GitHub this morning to conduct your midterm follow-up, you also downloaded the new material for that. So if you go in there, there's going to be a new script. So let me come here on my side to show you. So there was a new script in the 04 class code folder. That the script is called 0327 merge validation partial. You can copy that script. You can come to the main folder of the class and create a new project folder called 10 stability validation. So 10 stability validation is what you want to create. Inside of that, you can create the subfolders, code, data, and output. You can paste the code from GitHub inside of the code folder of that project. And then you can go ahead and create an RStudio project at the main folder of this new project that we're going to start. All right, so this time we really are not going to need to have any new data in the data folder because we're going to be just pulling data that we have already processed in the past. So that's going to be our goal. Once you have created the project here, the RStudio project, and also move that partial script inside of the code folder, go ahead and launch this RStudio project so we can get started with it. If you're not seeing the script there yet, which you may not, make sure you go under the Files tab, click on the R blue button, and then navigate to your code so you launch the partial code. All right, so before I start here, just want to make sure, give a moment here. If anyone has not been able to get to this point, I can give you another moment here. Just let me know if you need that time. All right, and just to make sure, in Tifton, can you all see my screen? If someone in Tifton can confirm if you can see my screen. Okay, awesome.
Yes.
Thank you. Okay, so yeah, so for this exercise here, our goal is to import all the previously processed, which means that clean interpolated layers that we did for yield, for terrain variables, and for electroconductivity variables, spatially join all of them, and then conduct the validation of the spatial temporal stability zones. So we're going to try to understand if, based on the variables we do have about terrain and electroconductivity, if we can see patterns of those variables on the different yield stability zones that we created already. So first chunk here is just loading all of our packages. I left that for you. You can just go ahead and play the chunk. If there is any package that it says you don't have, I think you should have all of it, but you know, if you don't have a given package, just go ahead and do the install.packages function. Next, we're gonna be loading here the theme of our map, which I also left for you, is just a whole bunch of customizations of how I want our maps to look like. So we're gonna use that. Okay, so as I was telling you, the goal is to import all the data sets that we use up until this point. The first one, so we're gonna bring in the spatial temporal yield stability zones, the terrain variables, and the soil EC variables as well. So let's begin here with the spatial temporal yield stability zones. If you come here in this next chunk, we're gonna bring that in and assign that to this object called STY_V. That basically stands for spatial temporal yield, and the V stands for vector, right? As you remember, we were exporting these layers all as in a vector format as GeoJSON. So if you give a tilde assignment symbol here, we're gonna use the function readsf for all of these, because again, they are of geospatial vector type. You open and close quotation marks. We're gonna have to navigate the folders where we exported those files individually, right? So right now, we need to get outside of the code folder. So if you do .. and hit tab, you're gonna be at the main folder of this project. We actually want to get out another level so we can see all the projects, not just the 10. So if we do .. again, now we can visualize all of the previous objects, or I'm sorry, all of the previous projects in this in your class folder. The one that has this layer here is under 07 wheel monitor. So you can navigate to that and click return. If you push tab again, you're gonna see the subfolders of that project. We want to go inside of the data folder, and then hit tab again, and we want to bring the sy_all.geojson. That's the one that we exported when we did that exercise. So if you run this and you print it, so first off, it is a simple feature object. In my case, it has 4,046 rows. In your case, it's going to be a little bit different, again, because of the grid size, which depended on the boundary. And it should already be in a projected CRS, because that's how we export it. And then if we look into the data side of it, we have the standardized yield for 17, for 19, and 20. Those are the years. We have the mean pixel, which is basically the mean across those two columns. We have the standard deviation of those pixels and the coefficient of variation. And if you remember, and I hope that by now you remember this very well, we use the mean pixel value and the CV value to create the 4 classes. So if a pixel had a CV greater than 30%, it would have been classified as ST class, as unstable or unstable, or I think unstable is what we used. If it had a CV of the pixel less than 30%, then we looked into the mean pixel. If that mean pixel was more than 120%, it was high yielding stable. If it was between 120 and 80%, it was medium stable. And if it was below 80%, it was low stable, right? So those are the classes that we have here that we already created and exported on this file that we just want to bring in here so we can validate them, understand what are the main drivers of those classes. All right, so the next chunk here, we want to bring all the terrain variables that we already cleaned and processed. So we're going to use a very similar approach. Give it the assignment symbol. Let's use read_SF. Again, open and close quotation marks. We're going to navigate to that project, which is a different one than the yield one. So .. to get outside of the code folder, .. to get outside of that project, of this current project, that 10 stability validation project. Now we want to navigate to the 08 terrain project, which is where this layer is. And if we hit tab again, this is going to be in the data folder. And if you hit tab again, this is going to be the terrain_v.geojson. That is the file that we have already in that project. We have already imported, processed, and exported this file here. So if you read this in and you print it, it's also a simple feature collection. It has the same number of rows as the yield. And remember, this here should happen, right? All of these layers should have the same number of rows. The reason for that is because we use the same grid every time to do the interpolation. So the grid was fixed, it's just the data behind it was changing, meaning that the number of cells in the grid was always the same, was in my case, always 4046. In your case, may have been a different number. And then if we look on the data side, we have elevation, slope, aspect, flow direction, and that's all. So those were the things we calculated from this layer. Now, if you go on the next chunk, is when we're going to import the electroconductivity process layer and assign that to an object called ECA_V. So if you give it the assignment symbol, the function that we're going to use is read_SF as well, as we've done previously. Open and close quotation marks. We're going to navigate to that project. So // gets us outside of the code folder. Another // gets us outside of this current project. The ECA data is in the 09 soil EC folder. So we want to get inside of that. If you hit tab again, you are inside of that project. We want to go in the data folder. Then if you hit tab one last time, it's going to be that ECA_V geo.geojson. That's the file we want to bring in. So if we read that and you print it, again, SF object, 4046 rows in my case, the same as the previous ones, projected CRS. On the data table side, we have ECA 30 and ECA 90, meaning the different depths, so shallow and deep ECA, and then the geometry. Okay, so, just taking a quick recap here. So we did all the processing of these different layers in their specific respective projects and exported those files in those projects. Now we're just bringing them in all in the same script, in the same R environment, so we can merge them. We can make a spatial join and have all of them in the same object. So then we can do some analysis. Was everyone able to get to this point and import the data? I guess if you were not able, let me know. All right, I don't hear anything, so let's keep moving. The last thing we want to import here, which is not really for joining purposes, is more for mapping and plotting purposes, is I want to bring in the boundary. So if you come to this chunk here, we're again going to use read_SF. You open and close quotation marks. Again, outside of the code folder, // hit tab, // again. The boundary is going to be in that 05 digitizing project. I think in that case, it's not on the data folder. I think it's in the output folder. That's how we exported it. And it should be the boundary.geojson. So if you bring that in, this is just the boundary, right? So it is a simple feature object, but just has one feature, which is just that one polygon for the boundary. And it is in WGS 84. Just to keep it consistent with the other layers that are all in UTM, let's just transform this to the same CRS as the other layers have. Again, we're going to use the st_transform. That's because this layer already has a CRS, right? So we don't have to assign a CRS, already has it. We just want to transform into a different one. So we're going to use st_transform. The argument is called CRS, and the EPSG code for that is 6345. So notice how we're reading that layer here, and also kind of like on the fly on the same chunk, we're just transforming that as well. So if you run that and you print it, now it should say CRS projected UTM zone 16 north. Okay, so we brought all these layers, we brought the boundary. Now the next step is gonna be to join all these layers into the same object. I basically left you here the code because we already done this function. I have used this function before and done this process in different cases. But just as a quick recap of what the code is doing, we're starting with STYV, right, which is the one that has the yield information. We're doing an ST join on the terrain, and then after that, a nasty join on the EC, which are all the three layers we have here to combine into one. Remember that a couple of arguments we're changing here on the ST join is we want the join to be using the function ST equals, as that is what we need in our case. And then we're doing a left join by saying left equals true. At the end here, there's a new function that maybe I have not showed you yet. So if I just do the join at this point without that relocate, so I block the code from flowing to the relocates. What happens is we have the first layers for so all the columns on the STYV, right? So that was all the EO data. And then I have a geometry here for that EO data. And then I have all the other columns after that. I'm just using this relocate here to change the geometry column from being kind of in the middle of the columns to actually be at the end of it, which is going to be useful for us if we want to use the colon notation to select columns as we did in the past. So if you let this the pipe flow through the relocate, it's just going to relocate this geometry column at the end of as the last column in this data frame. Just run that and you print it. You should have that happen. So geometry is in the last column now. And just a reminder here, so you're not going to have the 4,046 rows that I do, most likely. It's going to be a different number. But the most important point is that you have the same number of rows across all of these layers. If you do not have, then something went wrong on your side in one of the projects where that number is not the same. Right, so I would say just make sure that as you're bringing these layers, you do print them and you check the number of rows. You want this number to be the same for all three layers on your side. If that is not the case, let me know because I can try to help you to troubleshoot. We're not going to troubleshoot in class, but I can meet with you afterwards and we can walk through your code. And if you have that issue, it's important for you to fix it because otherwise you're going to just run into issues from this point on. All right, so, well, I guess if I just give a brief moment here just to ask, is anyone having issues with their number of rows not matching? Yes.
And I saw it in the previous exercise as a reminder. Why did it join? So I didn't have the EC.
Okay. Is that other people? So Renalisa here is saying that when she brought in the ECA, she only has the shallow one. So when on that project, the deep one did not come along. Did that happen to anyone else? Okay, Neva is waving yes. Anyone else having the same issue? Okay. So if everyone had the issue, then probably I forgot to teach you a part of the code, since maybe it seems like it's not everyone, maybe it was something specific on your side, and we can check your code afterwards. For now, I think we can keep moving because I think this may not cause you issues, at least not to the extent we're going to be able to finish today in class. So I can get with you after class and check your code to see why that happened. All right, so now we basically have this unified object that's called all_v that has all the data we need in one object, right? This was maybe the reason why I wanted to keep those layers as a vector geospatial file type and not as a raster, because it becomes really easy for you to see the data frame behind it and really see like all the columns side by side, all the values all the way down. So it's easier to visually assess that these columns are combined on a geospatial aspect and also having the data for you to see. So now that we have this object here where we have everything we need in one, we're going to export this so this current exercise, we're going to be doing more stuff. But we're also going to need this unified object in the future exercises that are going to come in this class. So again, we don't want to be bringing every time all three data sets and merging whenever we need. We do that once in this script, we export it, and then we have access to this unified data set as we need again in the future. So in the next chunk here, we're going to export that. So we're going to use, it is an SF object, so we're going to use a function write_SF. The first thing we give here is the object name, that is all_v, is the one we just created above. I want to break code just to make it a little bit easier to read the code. Open and close quotation marks. We want to get outside of the code folder, // We want to go inside of the data folder and export this as all_v.geojson. So the name of the file is going to be all_v and the extension is going to be geojson. Get outside of that. Remember that for write_sf, we always want to change delete_dsn to true. So if you run this, and now you go on the Files tab, go on the R blue button, go on your data folder, you should now see your all_v.geojson. All right, so the first part of this exercise, which was bringing all these layers, joining them, and exporting that joined product, we just finished. Now we're going to start working on the second part of this exercise, which is also within the same script, which is going to be to validate our yield spatial temporal stability zones with all the terrain and the EC data. This is a point where I just want to tell you that if you are doing this for a farm, for your study, for any other situation here, and you had other types of data, right? So let's say you had gridded soil data for that field, you would have done the same process as on a different project. You would have brought that yield data, or sorry, not yield, you would have brought that soils data, interpolated, exported to file. And then you would bring that in here, you would have those columns at this level here, where it would be soil, phosphorus, potassium, pH, texture, whatever it is. So you may have different layers for different situations, but the overall workflow looks very similar. All right, so first thing here, let's do some exploratory data analysis, as I always recommend you do. First off, using tables. So the summary here of this, we can just very quickly go through the summary here. So the standardized yield for 17, we see is ranging from 24 to 156%. That's what these columns are. For 19, from 6 to 178. For 2020, ranging from 33 to 154%. Overall, the mean of all those 3 years for a given pixel is ranging from 41 to 135% across all 3 years. Standard deviation you see here. The CV is ranging from 0 to 75%. So all these numbers making sense, right? We're just checking a sanity check to make sure that we didn't get any errors anywhere else. Elevation here for this field from 45 to 53 meters. So there is a gradient there. A slope from almost no slope to 7%. And then aspect full direction, we have those values there as well. Remember that aspect is in degrees, so it ranges from 0 to 360 degrees. And this is with north is 0 and 360. So I think that we had that question on that exercise. I was just reading more of that documentation to remind myself so I could remind you. So here is 0 and 360 is facing north on the aspect data. Full direction, we already talked about those values, how to interpret them. So we know that these are classes actually, even though here they show up as numerical. And then EC, we noticed that the shallow EC, we talked about that, was relatively lower. So ranging from about 1 to 9.8 on the shallow and ranging from about 2 to 15 on the deep. So we have, if you remember, higher EC, if we can assume that EC is being controlled by texture, then higher EC means finer soil texture. So more clay compared to sand, for example, right? So here is basically saying we probably have a top layer that's a little bit more coarser, and a deep layer that is a little bit finer in texture. All right, and if you recall, so now that we're bringing all this together, we have some NAs, but not in every column, right? So let's see, we start having NAs here on slope and aspect and some in flow direction, but we don't have NAs elsewhere. Again, if you remember, the reason for that is because the slope and aspect require, the algorithm that calculates them requires for the cell that you're calculating for to have neighboring cells. And near the border of the field, we don't have all neighboring cells, which ends up creating NAs in that case. So that's why we have some NAs on slope and aspects. Okay, so first thing here for us to just bring it all together again is I want to start making some maps that we're going to combine in the end and export. So we're going to develop this first map here for the stability classes. And then we're just gonna adapt that for the other variables one by one. So if you come here with me on this first chunk, let's start. We're gonna create a ggplot and then assign that to this object so we can call it again later in the script. So if you just give it the assignment symbol, we're gonna start with the ggplot call. We're gonna use here geom_sf, right? Because we have an SF object. So geom_sf. I want to say data is going to be equal to, we want to use here the all_v, which again is that data that has all the layers together. I want to break code here just to make it a little bit easier to see. On the AES, so notice that now our all_v has a lot of columns, right? So we really need to specify on the AES which one I want to use for, in this case, the fill of those polygons. So I want to say fill equals to ST class, which is the column that has all the classes. So really our goal here is going to be to make a map where each one of the pixels is going to have one of four potential colors, where each one of the colors is one of the classes, right? So fill equals ST class. If you get outside of the AES, I just want to say color equals NA. So here, this is an SF object because each one of those cells is a polygon. So you see here that we're changing the fill. So the fill is the inner color, the inside color of that polygon. And the color argument is the outline color of that polygon. I just want that outline to not have color. Basically, that's the difference here between fill and color in this case. All right, if we run that and just print the map, this is what we see, right? So we see the four different colors being a different stability class. I do want to make some quick adjustments to make this plot more professional looking. So one of them is going to be changing for a colorblind safe scale. So we're going to call the function scale underscore fill underscore Viridis D for discrete. And I just want to, this was one of the questions on the exam, and I just want to stress this here again. Why are we using scale fill? Why is it not scale color? Basically, it's because fill is the variable that we're changing on the AES of a given geom. If we were changing color here inside of AES, then this would have been scale color, right? So that's how you know what type of aesthetics you should have here after the scale underscore is whichever one you're changing inside of the AES of a previous geom. All right, so if we run that and we just make the map very quickly, it changed to this scale or to this color scale here. Next thing is I want to bring in the boundary. So let's add a plus. We want to call geom_sf again. The boundary is coming from a different data frame, so we have to specify that. So data equals boundary underscore W. And then I want to say fill equals NA because I don't want it to hide behind the boundary all the ST class data. So we just say fill NA, so it does not have a fill. We can see through it. It's a very subtle difference, but now you can really see the outline of the boundary there. And now, lastly, I just want to apply our theme, which was an object that we called myTheme_map. So if you just add a plus, we're going to call myTheme_map. And that should apply the effects of the theme that we wanted for this field. All right, so we have this object now. My goal is to replicate a very similar plot, but for other variables. So you can just come here and copy, starting at ggplot, you can just copy all that. We're gonna go to the next chunk, which is gonna be the map for elevation. You can give it the assignment symbol and paste the code that you just got above. Now, we're gonna have to do a couple of changes here on this code, so it actually shows a map for elevation. Can someone help me out to figure what do we need to change in this code for this to be the map for elevation?
We need to change the ST class
Okay,
or
so what should go?
11_n.
Yes, that's correct, right? So if we print all v, which is the data that we're using on this geom, we want to plot elevation, which is under this column 11_m. Yep. Nice. Thanks, Vinicius. All right. I think there's still something we have to fix. Let's see. Let's try to run it and see if that works. Okay, it did not work. So here's the error. Continuous value supplied to discrete scale. Maybe this is not as clear, but so let me help you out here. When we chose scale fill varieties_d, this variety scale here is for discrete variables or categorical variables, which is what ST class was. Now elevation is not categorical anymore, it is numerical. So we need to just change that D for the _C option, which stands for continuous, and that should do the trick. So if you run that, then this is what you see. So here, I think we have not talked about this enough. So let me just bring this up for talk here. So if you just have scale fill varieties and then you just hit tab, you get varieties B, C, and D. D is for discrete, right? So that would be categorical variables like ST class. B and C are for continuous variables, where C creates this like continuous scale. As you can see here, there are no bins, there's just continuous numbers. And if you change to varieties_B, it is also for continuous variables, but it creates bins. So notice how it looks when we use the continuous. I'm going to run again with the B option and print it so you can see the difference. So notice how with the bin option, it basically creates bins where inside of each one of those bins, it has multiple continuous values that now are getting all the same color, right? So everything that's in between 45 and 47 is this dark purple here. Everything that's between 53 and 55 is going to be yellow. So this is what is happening. And it's just, a decision on how you want to present your map. Sometimes the continuous is what you want. Sometimes the bin is what you want. I think for this case here, I wanted to continue with the bin option. So make sure you change that to _B. We're just going to keep going with that. All right. So again, copy this code. Let's move to the next chunk. Yep. It's the same.
It looked like your color scale is just a little bit dark. Like that,
You mean like just overall everything looks darker? Yeah. It may be, I don't know, maybe related to just the display. But like if only one of them was different, then maybe that would have been more concerning, but. All right, so moving forward, we want to do the same thing for slope. So go ahead and give it the assignment symbol. You can paste the code as we had before. And what do we need to change here to make this become the slope map? Ujwal, what do you think?
So, inside here.
Yes, so instead of having 11_m in fill, we have slope. And slope is one of the columns inside of this all_v data set, right? So we have that column right there. That's the name we're changing here. So if you run that and you print it, this is what you should see. Maybe in this case here, just to show you, just for, I guess, for us to understand the difference again. If I change this to Viridis C for continuous, it looks like this. If we change it to B for continuous bend, then we create bends, and it kind of like, it does not change the data. It's just changing the way it's showing the data, right? So it's just sort of like smoothing out to some extent, if you use the bin option. But again, it's not changing the data itself. It's just changing the visualization of the data. All right, next one, if you just want to copy this code again, go to the next chunk, the aspect map, give the assignment symbol, paste the code. Now, let me ask someone else here, maybe online. Hejimar, what do you think we should do here to change this to the aspect map?
It's only changed the _map for perspective. I don't know.
Yeah, so the way we would see is we check again this data set we're using at this geom, which is all_v. And then we just browse here to look at the name of the columns. If we want to show now aspect, we have a column that's called aspect, right? So that's what we want to change here. Right, so make sure you all change your fill equals to aspect in this map and then run it. And this is what we get. So again, maybe for aspect here, let's change to the continuous, so Viridis C, just because, you know, we have more degrees to really look if we change this to Viridis C. This is what we would notice, right? So if north, so imagine here the north is an angle of 0, and as you move clockwise, the angle increases until it reaches 360 on the same spot as 0. So really here, the aspect is in which direction, what is the angle that each pixel is facing, right? So here we see that there's a lot of darker colors in this, especially in this part and in the top part as well. These colors here associated with lower degrees, which would be from 0 to, so if 0 and 90, right? So we have 90 degrees being this angle. So we see there's a lot of data that is below 100. So a lot of data that's actually facing east, right? There's a lot of pixels facing east on the aspect side, which I guess is also what we would expect since we know there's a gradient of elevation from west to east. So west is high elevation, east is lower. So water is moving from west to east, as we also saw on the full direction map as well. All right, so the next one here, if you just copy the code again and paste on the next chunk, I want to make a map for ECA shallow, so ECA 30. What I want to change here is just if you print all V, you're going to see that we have a column called ECA 30_DSM. We just want to change that as part of our fill. So if you run that and you print it, now you have your ECA 30. Let me try to make this Viridis B for bend and see if that looks, how that looks like. I guess it doesn't really matter. If you wanna, you know, use B or C, that's not gonna be something that is gonna change anything grade wise. So feel free to use whichever one you want in this case. In all these plots, actually. Just the first one has to be discrete. Everything else can be either B or C. All right, so this is the map for the shallow ECA. You can copy this one last time and paste on the chunk below for the deep ECA, the ECA 90. Where again, the only difference is just the fill variable. We want to have fill equals ECA 90. So if you print that, if you run that and print it, this is what we see. Let me change this to, in my side, I want to change both of the EC maps to continuous. You can do whatever you wish on your side. All right, so now we basically have, I think, 5 maps we just created. So yield, elevation, slope, aspect, ECA, 6 maps. So ECA shallow and deep. So we have 6 maps that now I want to combine them into one, and I want to save this to file. So imagine you would potentially use this as, you know, for a publication or maybe a presentation. Because in the beginning of the script, we loaded the package patchwork, we're going to use patchwork notation to combine these plots. So the way the patchwork works is if you add a plus, it's going to put that object that has a plot right next to it, so on the same row. And if you want to have multiple rows, you add a / to mean break line. So if you run this code here, what you're going to see is this, which right here is kind of ugly looking, but once we export to files, is going to be nicer, better configured, I guess. But basically we have the classes ECA 30 and ECA 90 on the first row, so on top. And then on the second row here of plots, we have elevation, slope, and aspect. So we're keeping ST class and EC variables in the same row and all terrain variables on the second row. So if you run this code here, which again is only working because we have patchwork loaded as a package, and then you do a ggSave that I left you the code already, this will export the combination of all those plots as one to file. So if you come on your Files tab, our blue button, you go on the output folder, you have this allmaps.png file, which is what we just created with this ggSave. And if you open that, it's going to look more professional, I guess, and not squeezed as it looked in the chunks. So basically we have, you know, this would be a plot that you could show all the layers you're using for a given exercise. You could do something like this. So I have this question here, which I'm not going to ask anyone to answer, but just for us to think. So if you look at the stability classes map, which is the first one, does it seem like there's any relationship of other variables with it, just visually, I guess? You know, we can take just a quick moment here just to assess that. I guess I can see some patterns here, but I'm not quite sure if they are actually significant patterns. All right, so I want to close this and just continue with our exercise, which now really I want to validate these zones. So I want to go on a given pixel. So let's say, let me just open this map here again. So for each pixel here, so let's say we think about the unstable first. Every pixel that is yellow on the unstable map, I want to extract only for those unstable pixels all the underlying data related for ECA 30, 90, and terrain variables, in a way that I'm going to basically group all the data that belongs to a same stability class, and then have that data there and compare it with the other classes and understand if they are different or not. Like if the variables that we have here, the electroconductivity variables and terrain variables, can help us understand why these classes are, why are they high stable? Why are they low stable or unstable? What is making them to be stable or unstable in different yield levels? So I left you the code here because there's a lot of things going on. I will tell you what is going on. I did not want to ask you to make the code yourself or with me in class, because this code is a little bit more complicated than you know, really you needed to understand. But basically, I'm just automating the process of creating many plots. So where, imagine now that I'm gonna have, so here's the plot that I wanna have. On the x-axis, I wanna have the stability classes of unstable, low stable, medium stable, high stable. On the y-axis, I wanna have first, let's say, slope, and then I wanna have a same plot but separate with aspect, and then another one with ECA, right? So this code here is just automating that for us and making things look nicer. So I'm leaving flow direction outside. I'm using the factor function here to change the levels that appear. So whenever I plot ST class, it's going to show them in the x-axis in alphabetical order, meaning that it's gonna be first high stable and then low stable and then medium stable and then unstable. So the order is not logical. So I'm just changing that order in the way that appears on the plot. On this part of the code, I'm leaving flow direction out. I'm doing a pivot longer, so I have all those variables, the terrain and EC variables pivoted longer. I'm changing the levels of those variables so they appear more in an order that makes more sense to me, with elevation, slope, and aspect first, and then ECA after. And then plugging that into a ggplot, where I'm using a geobox plot to show the distribution of the data, and doing a facet wrap by the variable name, which is basically all these levels here. So again, you don't really need to understand what the code is doing, but if you're curious, you can play around with the code on your own. But if I just run that chunk, this is what we're gonna see. So we have 5 panels, 1 panel for each of our field variables of elevation, slope, aspect, and both depths of ECA. And then we're looking at these box plots where each box plot, so if we look at this first one here, elevation, we have 4 box plots where each one is for one of the classes, the stability classes, right? So low stable, medium, high stable, and unstable. And we're really looking at it, looking at the distribution of elevation for each one of those classes. So again, what we're doing here is basically taking all pixels that were classified in a given stability class, and then looking at what was the value of that same pixel for all of these different layers, grouping them, making these box plots, just to see if we can find patterns. All right, so, you know, maybe let me ask someone here, if just visually inspecting it, does it seem like one or more of these variables may be controlling what is the class that a given pixel belongs to? Doug, what do you think? Sendes, what do you think? What did you say? Sorry. No idea? Neva. So by looking at each individual panel here, does it seem like one of these variables of elevation, slope, aspect, and EC is having an impact on what is the final class? No thoughts? Let's see in Tifton. Dalton, what do you think?
I'm got some issues right now with my code, and that's what I'm trying to fix. I had the different row lengths, and I'm trying to go back and fix it, so I haven't.
Okay. Yeah, I mean, if for some reason it doesn't work, I can help you out afterwards. But you know, if you just look at the plot that I made here, do you think that any of these variables here are differentiating the different stability classes?
Maybe elevation is kind of got the same trend.
So what do you
but
see?
not really. Just with their orange box kind of being the highest on elevation, being the same as the high stable for your aspect.
Yeah, I agree. So it seems like if we look at elevation, maybe it's the clearest one to visually assess that the high stable class, which is the one that has the purple box plots, seems to have a very high elevation compared to others, right? So low stable has very low elevation. High stable has higher elevation. And then unstable perhaps is actually maybe the lowest ones of this box plot distribution here. Yeah, so I mean, everything here may also be having an impact. It's just that we are not able to, so we're not comparing them statistically yet. We're just visually assessing, right? So one way that I want to explore this next is just for us to actually run analysis of variance. So imagine that now for each one of these plots that you're seeing, we're actually going to be running that analysis. So we're going to be explaining, so elevation being explained by ST class would be the first one. And then we're going to be able to put letters here to understand if these differences that we're seeing are significantly different or not. So if the box plots have a significantly different mean from each other within each one of these variables. So that's what we're going to do in the next chunk here. Okay, so again, the next chunk is more complicated than this class covers. So I want to explain to you what's going on. I'm not gonna walk, you know what, actually, I think this is probably a good stopping point for us to just. Yeah, I think this is a good stopping point for us to continue on Friday. So what I want to ask you to do still today, so you're ready for Friday, is if you come here, so on your outline, if you go on the ANOVAs, there are some packages here that I don't think we used yet in this class. So if you do not have these packages installed, so you can try to load them here first, going one by one. So e-means, multicomp, per, and car. If any of these packages here comes back with an error saying could not find the package, then it means you don't have it installed. Then I would tell you to just uncomment whatever package you don't have, install it, run only that line of code, install it, comment it again, so you inhibit that from running in the future. And just make sure you do that for previous class, because then we can just come here and do a run all chunks and start from here. But basically, what we're going to be doing is running analysis of variance for each one of these and adding the letters there, so we can actually check if those box plot means are different from each other or not, and then really be able to tell, characterize or give context to these yield stability classes and say, we're going to be able to say on the high stable class, I see that it had a significantly higher elevation, lower slope, and so on. We're going to be able to characterize those classes with the variables that we have available. Yeah, so I guess for today, we can probably just stop here, make sure you install the packages that you need. And then let me take your attendance before we wrap up.
Dr. Bastos, I was able to get the email to finally go through.
Okay, nice. I'll double check on that here. Thanks, Clint. All right, so please go ahead and claim your attendance. And if anyone has any questions, I'll be here. If anyone has any code issues and you have time to go through that now, I can help you. And for those that don't have issues or don't have questions, after you claim your attendance, class is dismissed. Thanks, everyone. Anyone in Tifton has any questions or issues?
Yeah, so to fix my stuff, I'm about to have to go take a midterm, so I can't stay right now, but can we meet anytime between now and Friday before class to figure it out? Or can I send it to you or what?
Yeah.
I think something in my ECA.
if you can send me email first, then I can see if I can help you by email. And if it seems like more complicated than that, then we can set up a Zoom call as well.
Okay.
All right. Thanks, everyone. See you on Friday.